Hello, everyone. First, I'd like to thank you all for coming here, and thank you for everyone who helped getting me here. It's always a real treat for me to be able to be let out of the dungeon that is NERSC and talk to people who appreciate technology, but in the context that is greater than the world of HPC, which is what the world I live in is. So as Young said, I work in the Advanced Technologies Group at the National Energy Research Scientific Computing Center, otherwise known as NERSC at Lawrence Berkeley National Laboratory. This is our building. And for those of you with a keen eye, you might be able to tell that we are located up in the Berkeley Hills, overlooking the UC Berkeley campus. This is the Campanile. For those of you who may be familiar with Berkeley, this is the Bay Bridge. And on a very clear morning when I come into work, I can stick my head up out of my cubicle and see the Bay Bridge, the Golden Gate Bridge, and the Richmond Bridge all from my desk. It's a beautiful location, and I invite you all to come check us out. We are a completely open and unclassified laboratory, which plays an important part in what I'll be discussing in terms of our technological requirements. But I'm not here to talk about our view, as nice as it is. I'm here to talk about technology and the way that we use technology that's provided by companies like Samsung and others and integrate them into high-performance computing systems or supercomputers to solve the world's leading scientific challenges. So I work at NERSC. And for those of you who may not be familiar with it, NERSC is the mission computing facility for the United States Department of Energy's Office of Science. So it is our job to provide computing resources that are world-class at solving high-performance computational challenges as they are applied to science. So it is our job to provide supercomputing resources and data and analytics resources for any researcher in the US who's funded by the US Department of Energy's Office of Science, whose scientific computations cannot be addressed by the needs or be addressed by campus or regional scale supercomputers and really need a world-class instrument to do the science that they do. So like I said, NERSC is a part of the DOE Office of Science, and the DOE Office of Science is a part of the Department of Energy that does, it funds basic research in pretty much every scientific domain you can imagine. So people jokingly say that DOE stands for Department of Everything because of this. So here's a few highlights of the areas in which the US Department of Energy Office of Science funds research. So we're covering everything from bioenergy. So this would be, sources of biofuels that help secure our future in clean energy. To things that you might expect from something called Department of Energy, like fusion science. So how can we understand the fundamental properties of what's happening in fusion plasmas inside fusion reactors, to more abstract things that are really fundamental, such as cosmology. What is the nature of the universe, and how do we mathematically define fundamental constants that are intrinsic to the fabric of our universe that we live in? So it's a very broad scope. In terms of what NERSC has to do, is because we need to provide computing and data analysis resources that meet the needs of all of these research areas and all of these researchers. So as a result of the very broad scope of what the Office of Science funds in terms of researchers, we as a center support a broad user base in terms of scientific computing resources and the sorts of jobs and science that we support. So just some speeds and feeds from 2018. So this is our last year operational assessment. I pulled these numbers. We had 7,000 active users with accounts. A little more than half of those users logged in and submitted jobs over that last year. So over 4,000 users actually running jobs in our systems. We supported 700 different scientific projects and about 700 different applications along with those projects. And we're a highly productive center. One of our points of pride is that our users publish over 2,500 peer-reviewed publications in various leading journals around the world, and credit our resources as being a critical part of enabling their research. From a technological standpoint, again, some speeds and feeds just to give you an idea of the scale at which we operate. We delivered about 6 billion CPU hours last year to users. So this is cycles spent doing scientific computation. About 25% of those hours are spent on simulations that use 1/8 of our system at once to solve a single problem or larger. And the speeds and feeds of I/O in terms of data flow and the amount of data that we handle. So we have, as I'll say in the next slide, we have an NVMe-based file system, which we call the burst buffer, and that saw about 140 petabytes of I/O traffic last year. We have an all-disk parallel file system. It's about 30 petabytes. It saw 850 petabytes of traffic over 2018. We have a tape-based archive, 60 petabytes of total traffic. And traffic to the outside world outside of our center totaled up to about 10 petabytes of data coming into and out of our facility from other places. So our utilization is extremely high because we support so many users and our resources are in such high demand. So we're looking at between 90 and 98% resource utilization on average over the entire calendar year. The lower number, 90%, is if you include scheduled downtime for maintenance. 98% is if you exclude it. So 98% of the cycles that we plan to have available are actually used by our users. And our uptime is certainly not what you may be accustomed to if you work in the hyperscale space. We're sitting between 1 and 3 nines, depending on if you're looking at the compute system or various storage systems. But this is about what we operate at on an annual basis. So to enable all of this science and deliver these cycles and these resources to our researchers that we support, we have a number of big systems. Our flagship system right now sitting on our floor today is named Cori. It's a Cray XC40 system. So this is Cori up here. You can see a row of cabinets. These are 10 cabinets wide, and then they go 6 rows back. So it's about 64 cabinets like this. Each one is about $1 million. And they're packed with compute nodes, networking, NVMe. And as I listed up here, there's about 12,000 compute nodes, about 9.6 thousand of which are supporting Intel Knights Landing processors, and the remainder are Intel Haswell-based Xeon processors. And there's integrated DRAM, as all systems today have, but it also was one of the first systems to field on-package memory in the form of MCDRAM, which is a variant of Hybrid Memory Cube. So in terms of data resources that support the computations that happen on the system, we have a 1.8 petabyte all NVMe burst buffer, which is integrated throughout the Cori system. The way this is used is that users can request a certain slice of this NVMe for their job, and when their job launches, they can read and write to the all NVMe file system that was created just for their job on demand. Just beneath that, we have a 30 petabyte all disk parallel file system based on Lustre, and it can deliver 700 gigabytes per second to a single application. This is read and write. And then below that, we have a higher capacity storage tier coming in, 75 petabytes, again, all disk. And then at the very bottom of the scale, we have a tape-based archive, which today sits at about 150 petabytes used, and we expect that to grow to about an exabyte over the course of the next 3 years. So the technology is fun. I love talking about the technology, but ultimately it's not what leads me to come to work every day. Really, the majority of the people that work in NERSC are really motivated by the science that we enable. So I wanted to walk through some of the scientific projects that happened over the last year that really highlight what we do and what our technology provides. So the first of which is kind of a traditional HPC style application. And the scientific motivation of this project was to see what would happen if the Hayward Fault, which runs along the East Bay here, would have a massive earthquake or a significant event happen. What would the impact be on really our society and the infrastructure and the buildings, and what would be the societal impact of such an event? And this is extremely relevant because the Hayward Fault historically has ruptured once every 150 years or so, and we just passed the 150th anniversary since the last major event. So we are now in kind of dangerous territory, and that something is likely to happen on this fault. And the researchers who did this study, McCallan and his colleagues, wanted to understand and be better prepared to understand where the damage would be likely to occur. So he did broadband earthquake simulations. Now, earthquake simulations have been done on HPC for a long time, but what's unique about this work is, one, it's a broadband simulation that went up to 5 hertz. So the ground motions that they were simulating were vibrating at up to 5 hertz. And the gold standard of earthquake simulation has historically been 1 hertz. And 1 hertz is fine if you want to understand the damage to large buildings, skyscrapers, and bridges. But the 1 hertz vibrations that earthquakes produce don't actually impact shorter buildings. You need to go to higher frequencies to actually capture the effects of that damage. And the higher frequency that you simulate, the more computational demand is required to conduct that simulation. And it's a nonlinear computational complexity scaling with frequency. So he did a massive scale earthquake simulation of the entire East Bay, simulating a Hayward Fault event. And then what he did was he took the output of this broadband simulation and then applied a building simulation or a suite of building simulations on top of that and simulated what would the effect of those vibrations be on buildings of different sizes that were scattered throughout the whole Bay Area. And understand how do those vibrations in different parts of the Bay and the geophysics underlying those vibrations, what kind of damage does it do to tall buildings, to short buildings, to everything in between, so you could better understand where would damage be most significant and what would the effect of such an earthquake be. And this was enabled by using over 500,000 CPU cores. The simulation ran for about 9 hours. That was to simulate the actual earthquake hazard. And then to measure the effect on buildings, there was a second simulation that took the output of that first simulation and did the building simulations. That ran at a much more modest scale. But one of the key limiting factors here was I/O. So I went back and looked at this actual job and the telemetry we collect on our systems, and I saw that his burst I/O rate, so this simulation, the earthquake simulation, was writing at over 800 gigabytes per second to our NVMe, and this wouldn't have been possible on our all-disk file system. So in addition to traditional simulation and modeling work, we also are beginning to support a lot of experimental data analysis workloads. So this slide highlights a recent experiment that was done at SLAC National Laboratory, which is located at Stanford, near here. And at SLAC, they have a very big, it's called LCLS, the Line Coherent Light Source. It's a linear accelerator that generates very powerful X-rays. And one of the instruments that they can attach to this is called an X-ray free electron laser. And they used this X-ray free electron laser at SLAC to image a protein complex called photosystem 2. And this is a protein complex that's found in algae and many types of plants. And this is the molecule that's responsible for taking a ray of sunlight and splitting a water molecule and producing oxygen. And this has tremendous impact for moving towards clean energy sources. You know, if we could do what plants do and convert sunlight into energy very efficiently, I mean, this would be transformative in our energy future. So this study was really to understand the fundamental processes of this reaction. Unfortunately, this reaction, it's a very complex molecule that causes all this to happen, and the reaction happens on the order of 1 to the minus 15 seconds. So it's extremely fast, and it's extremely small, and it's extremely complicated. So what Yachandra and colleagues did at SLAC was they imaged this reaction happening using the X-ray free electron laser at SLAC. And this is using very high intensity X-ray laser running at very high frequency, so they can actually get images as the reaction is happening. So one of these shots at the X-ray free electron laser runs for about 5 minutes, and it generates between 60 and 100 gigabytes of data. But that data doesn't come out as a nice picture of the molecule of what's happening. It comes out looking like this diffraction pattern in the bottom right here. And in order to turn that diffraction pattern into something useful, there's a mathematical transformation that has to happen to turn that from Fourier space into something that is in real space. And that is computationally very expensive when you have to do it over 60 gigabytes of data every 5 minutes. So what they did was they beamed this data that was coming off every 5 minutes to NERSC into our Cori system, used our Cori system to process and do this mathematical transformation to get the electron density while this reaction was happening, send the results back to the instrument at Stanford, and all of this happened within 15 minutes so that they could prepare the next 5-minute shot based on the output of the previous one. So this is a case where experiment and supercomputing is very tightly coupled so that we can use supercomputers to steer an experiment as it's happening. And then finally, in addition to experimental data analysis and modeling and simulation, we're also seeing a growth in AI, and specifically AI to enable scientific discovery. This work was done by my colleagues Debbie Bard, as well as a multitude of collaborators at Intel and Cray. And what they did was they wanted to understand some really fundamental properties of the universe. What is the nature of dark energy? We know it exists, but we really don't know very much about it, other than it causes things to happen in a way that we physically don't understand. So this was a really interesting study where they did an ensemble simulation of a whole bunch of different replica universes. They did about 100,000 different versions of the universe, all with slightly different fundamental parameters governing the dark energy behavior. And then they compared this data to what was observed from the Planck telescope, which is a telescope operated, it's orbiting Earth, I believe, by Europe. And then they use deep learning to infer with higher precision what some of the fundamental parameters that govern our current understanding of dark energy are. And they were able to use AI to both do training on their simulation outputs as well as inference to achieve a better understanding of what the parameters must be to actually match the experimental data that was observed by the Planck telescope. And again, this was a case where the AI was really limited by the rate at which we could pull data, the training data, off of persistent storage, and they made heavy use of the burst buffer as an enabling technology to really do this at this scale. And again, speeds and feeds, they used between 150,000 and 500,000 CPU cores. They trained on 1.4 terabytes of training data, and they were able to sustain about 3.5 petaflops of single precision, so not half precision, performance over the course of this training run. So this is kind of an overview of all the different types of science that we do and the different motifs. But if you take a look at what's happening technologically, there's an underlying pattern of scientific workflows that all of these follow. So that's what I want to talk about as we get closer to actually how we integrate technology to solve scientific problems like this. So scientific workflows, no matter what science problem they're trying to solve, are ultimately tied together by the data. So a simulation inputs data, it modifies that data, it outputs that data. AI will read in data and it'll train something and then infer data that's written out. And all of these processes can be stitched together with the unifying attribute of the data that flows through this. So we tend to look at workflows and scientific workflows in the context of how that data moves around. In particular, as a result of economics, we tend to have multiple tiers of data. I showed you the pictures of the systems we have on the floor today, and we can think about the data hierarchy in our data center as being in 3 or 4 parts. At the very top is the most extremely fast place to put data. It's very precious, it's very expensive, and that is memory. And that's exactly where CPU processors retrieve data that they're going to compute on and write it back out. And of course, memory is volatile. It goes away if you lose a node. So a single flipped bit can ruin an entire simulation that's using the entire system. So we have persistent tiers below that. We have a scratch space where data can live for on the order of weeks as multiple jobs read and write this data. Below that, we have a project space, which is where valuable data is stored by scientists. So after their workflow is done, they keep it there. And then the very cold tier is an archive. And this is where data goes to live forever. So it may not be valuable tomorrow, may not be valuable next year, but at some point in the future, this is a valuable data set that shouldn't be lost. And we support storing data in all of these tiers. But let's look at how a prototypical scientific workflow actually uses and interacts with all these tiers of storage. So the first step in just about any scientific workflow is that data arrives from somewhere. This is the input data that is the beginning of scientific discovery. This is an optional step. Sometimes the data is generated inside the system itself. So if you're simulating something like a crystal, you can mathematically build a crystal using an algorithm, and you don't need to load a giant data set from somewhere else. But in many cases, such as the AI case or the case with the X-ray free electron laser, data arrives from the outside world. So it might come from the wide area network, and this usually happens in the form of files. So files are sent to us, into our center, and land somewhere on storage. They don't land in memory because you wouldn't want to lose that data if a node shuts off for whatever reason. So it lands somewhere in our storage hierarchy, and that's when the actual workflow can kick off. So when the workflow launches, what a user actually does is they write a script. It's written in something like Bash, so very basic. There's nothing magical about it. And their Bash script, has the commands necessary to run a parallel application, but also has some special pragmas in it that indicate how much resources they want this job to be allocated. So this includes how many nodes they want, how much burst buffer capacity or NVMe capacity they might want, and how long they expect this job to run. They submit that to the batch system, and we run a time-shared system, so their job might run in a few seconds. It might take a week for their job to work through the queue, but then it's launched, and then our supercomputer's resource manager does wire up. So all of the communication done by our scientific applications happens via remote direct memory access, RDMA. So there is some special wire up that has to be done so that the job nodes can communicate with each other and share memory. And then the application, after it's wired up, it starts. And every process that's launched reads the input data that was beamed in. And this could happen in any number of ways, but because data is most often in the form of files, usually every process is reading its input data from a very large file. or many small files. But in either case, they know what slice of data they want to read. They read it into their memory, and then the computation begins. And then as the workflow executes, this process of launching jobs might happen once, and that might be the whole workflow, or it might be a chain of jobs, such as in the earthquake simulation case, where there was one big simulation that produced the vibrations, and then a second job would have to come in and read those vibrations, and then do calculations to understand how those would affect buildings. So during the workflow execution, parallel applications read and write data, and this data could be data for primary analysis, so understanding how much is the building dipping and deforming. It could be state, so because we run jobs over thousands of nodes, if one node crashes, there's really not a lot of resilience built in, the whole job crashes. So you don't want to run a job for 47 hours, and right before it's about to finish at that 48th hour, have a node pop, and then you lost all of that data. So there's defensive I/O that happens quite a lot, where state is being dumped out to a file system sufficient so that if something does crashes, the simulation can resume from where it left off or where it last dumped its state. We call this checkpoint restart. And then it might also be outputting derived data. So this would be something that happens in situ that you don't necessarily need to write out all of memory, you just need to write out a few key values, and they might be read in by a separate job later on, or shared with the community, or so on. And the nature of this I/O varies widely. So parallel applications run in series, so you might have a very large simulation run and then another very large simulation pick up where that one left off. They could run in parallel, so a bunch of smaller simulations or calculations happening. And they might be using only a small part of the system, which is actually the most common case. They're using a couple hundred nodes at a time, or they might be using the entire system. And we are responsible for providing a resource that supports all of this. So once the simulation is, the workflow is complete in terms of computation, the useful data is staged out of this really hot scratch space because it tends to be very small in capacity. So we have to manage space on it and make sure there's always space for the next person who wants to run their calculation. So users will save their important data down to a colder tier while we purge the scratch space of data that's been sitting around for too long. And then finally, the last step is that value is extracted from this data from one way or another. This might be sharing the data with people, collaborators at other universities, other labs. It might mean feeding it to another pipeline or another workflow downstream that can derive some other useful information from it. Or it could just mean sticking in the tape archive and just figuring, well, it'll be useful when it's useful and we'll have it. So that's what the scientific workflow encapsulates. But there's a number of things that aren't included in a scientific workflow as they execute in our system. The first of which is provisioning virtual machines. So we don't expect users to be able to choose from an a la carte menu of every kind of virtual machine configuration they want to do their work. Instead, we provide a very limited node type, and they have to work within the constraints of that. Similarly, we don't expect them to set up the operating system, the runtime environment, or anything that would require administrator privileges. Because this is a shared resource, and we do have shared memory, for example, across nodes, there's a lot of security implications of letting users run wild with administrator access. So it's not part of what we do, and it never has been. But what we do nowadays, the users have more sophisticated software stacks, is we support Docker images. We don't support Docker as a runtime environment, but users can bring Docker images to us, and then we will unpack them onto nodes on demand as part of the job wire-up process, do a jailed route for them, and they can operate their Docker image within an environment that meets our security requirements. Sadly, there's no SLA for performance because this is fundamentally a shared resource that all users have access to. We can't guarantee that another user might be doing something bad and using all of the I/O bandwidth while you want to use some. Instead, what we do is we do provide support. So if you call or email NERSC as a user, within 4 business hours, you will get a response from us. And the people responding to our users oftentimes are PhDs in a domain science. So I'm a material scientist. We have nuclear physicists, high energy physicists on staff, chemists. We've got a very wide variety of domain expertise. And those are the people who are providing first-line support for our users when they have questions. So although we're not saying you're guaranteed to have this level of performance, it's perfectly valid to submit a ticket and say, hey, my job was slow today. What's going on? ? End. And you will get a reasonable response from someone who both understands what you're doing as a scientist and how the system operates. and give you some pointers as to what you might want to look at to figure out why it wasn't performing well that day. And then finally, users don't come to us with a credit card. There's no exchange of actual currency involved. Instead, the currency that we offer our users are CPU hours. So they're given an allocation of, say, 5 million CPU hours, and they can spend this over the course of a year as they see fit. They can run on one CPU for 5 million hours, or 5 million CPUs for 1 hour, or anything in between. But we don't give out this currency. The DOE Office of Science program managers do. So they understand what science portfolio they want to promote, and they dictate how much resources at NERSC their researchers are able to get. So we don't really control who our users are, or what they do, or how much time or priority they're given. That's done by the program managers who understand the science that's being conducted on our systems. And really what this all means is that there's no assumption that our users are computer savvy in any way. They typically don't want to be. They want to do science. So it's not our job to tell them, hey, learn how to run a Linux operating system, learn how to tune kernel parameters and debug a network stack. We just provide a runtime environment where they can take their application and their workflow, set it down on the system, and with reading a very brief user guide and having a little background information about how HPC systems in general work, actually get productive use out of that system in very short order. So because our users don't provide this as part of their workflow, we as a center are responsible for doing that. And so let's talk about how those requirements manifest in real life. So because we're in charge of deciding node architecture, we ultimately have to decide what types of nodes to deploy. And usually we want as few different types of nodes as possible because we're in the game of providing a capability resource. And it's easier to run one job over 9,000 nodes of the same type than 9,000 nodes of 5 different types. So we really like to keep things as homogeneous as possible to enable large-scale science. Because users don't have anything to do with root, we're responsible for providing the OS, the runtimes, the file systems, and everything an application would have to interact with to get performance out of the system to do their science. Because we don't offer an SLA for performance, we have to figure out a best way to make sure that everyone gets a fair share of the resources they've requested and are not able to adversely impact other users who are also trying to use the system. And because they don't come to us with a credit card, it's upon us to figure out what the best value is and how we architect a system for value. Even though our system demand is at 98% utilization all the time, that doesn't mean we get more money to deploy more resources to drive that down. So our money comes from Congress. And we're ultimately, we can only operate within the budget that they give us. So it's up to us to decide how much of that money we spend on hardware, how much we spend on making the environment easier for users to run in, and how much we spend on developing new solutions that will make our users' lives easier in the future. And because our users are not assumed to be computer experts in any large way, we have to provide sensible defaults for pretty much everything that touches performance. But at the same time, we do have many users who are very sophisticated and actually write in assembly. So we need to support them too. So this means balancing sensible defaults as well as giving them as many knobs as they want to be able to tune the system if they are expert users. And all of this has to be scaled to hundreds of users running on our system at any given time, thousands of jobs running on our system at any given time, and many, many different levels of parallelism, all running concurrently on our system. So it's difficult to take all these constraints and design a single system to do it, but we have a general design strategy to support common workflow elements. So this means we have to deliver a POSIX file system to our users because that's what applications write against. Users know how to open files and close files and read files and write files, and that's a standard interface that every application we support uses. So we need to provide that as a resource for their applications to use. We also support many of the common runtime and compilers, C, C++, Fortran, and Python. And then for parallelism, we also provide the interfaces that applications use to get the most performance out of the network infrastructure that we have to enable cross-node communication. We also invest heavily in sustainable technologies. So we don't like building one-off snowflake systems because there's a tremendous amount of risk involved with that. We love open source and we love open standards where they apply because that gives us confidence that tomorrow, if a company disappears, we might still be able to pick up the software or the hardware that they're using and support it ourselves for the rest of the system. We also work closely with vendors for this very same reason. So we like to develop solutions with our vendors so that we understand the technology and can help steer it towards directions that benefit our users most. And then we also love products that have value outside of HPC because we're not the market leader. We don't steer the market anymore because we're not deploying at scales that rival Google and Amazon and so on and so forth. So we like to use whatever technologies they invest in wherever possible. And really what this all amounts to is maximize the amount of science per dollar that we get out of our system. So what this means in practice, if we need to decide the best choice of hardware, we're looking at hardware that delivers the best performance and extreme scalability. We're also looking for something that's very manageable, because every dollar that we spend on cheap hardware that requires a lot of people to manage is a dollar we could have spent on more expensive hardware that may require fewer full-time staff to operate. And it's this balance of value. Do we want to spend money on hardware or people, and which one gives us more science per dollar? We also need to focus on user productivity, and this is touching on that productive environment part. So like I said, our applications just use POSIX I/O. They need file systems, so we need to provide that. It's a hard requirement. Our users also like that data is just there. Tiers are generally not very user-friendly. If a user has to remember is the data they want stored on flash or on tape or on disk, that's complexity that they really don't need in their lives if they just want to run their calculation today. So the more we can consolidate tiers and just provide storage where their data is there and it performs well at a moment's notice, the better. And then whatever we provide, it must support all three of the workload types that we see at our center: simulation, experiment, and AI. And then value is kind of just falls from all this. We want to maximize the performance per dollar, but we also need to maximize the ease of use for our users and our staff. And then we also need to minimize the disruption for scientific workflows. So what users have been running, they want to continue to run tomorrow. And our systems, we can't dictate to our users that they need to change the way they do science simply because we don't have a system that supports the way they were doing it before. So we really need to minimize the amount of burden that we put on our users who are using our system as we deploy new systems. So if you look at these requirements, some technologies really jump out very quickly. For performance and versatility, NVMe, when designing a storage system for 2020, is the obvious choice. For the ease of use and keeping in with what scientists have always done, this means we have to use a file system. And for manageability and low cost, this really means we need to work with vendors who understand our needs and our unique operating requirements so that we can optimize the overall solution to be one that has minimal risk to us as well as requires minimal full-time staff to operate, so that we can then put those dollars into other places that more strategically benefit our users going forward. So it's clear that we need all NVMe high-performance parallel file system for our 2020 storage system. The question then becomes, how do we balance cost and usability? So in the interest of time, I won't belabor these points, but we did an extensive study when we set out to design our storage system for 2020. And it's documented in this paper that we just presented in Frankfurt a few weeks ago, where we looked at every aspect of our workload today in the I/O and the storage, and figured out, how much capacity do we need? And through some pretty simple math, we were able to figure out that 30 petabytes balances how much data users have to shuffle in and out with how much we could afford to deploy to enable that really high performance without users having to constantly shuffle data. Oh, figure disappeared here, that's a shame. We also looked at endurance, because the question is, do we want to spend the extra money on extreme endurance drives, or is one drive write per day good enough? And the answer is one drive write per day is good enough. If you look at how much our users actually write to our systems, it's about a petabyte a day on a 30 petabyte file system, far less than one drive write. And so this is the solution that we wound up with: 30 petabyte all Lustre file system, 7 million IOPS, and 4 terabytes per second performance to a single application. I will skip these. So that was our 2020 system, and we decided all flash was certainly feasible for 2020, but our job doesn't stop there. So the 2020 system, in my eyes, is kind of a done deal. It's designed, and we have a contract, and we've announced it, and all that has to happen is the system has to show up in the next year. I'm working on the next system now, the 2024 system, which we call NERSC 10, And this is the ultimate design goals are the same. We want high performance, we want ease of use, we want all the good things. The technologies are roughly the same. NVMe is the way to get performance and versatility. Persistent memory will likely be more viable at that time period. But the rest of these, in terms of managing risk and making it usable for our users and minimally disruptive, is not compatible with this technology. We're limited by file systems because they have fundamental limits in terms of how far you can scale them because of the way consistency is handled. So we have this vision for 2024 and 25 into the future of moving to objects and key values, but implementing a file system on top of that is just sort of another user interface that's like middleware. So users don't have to realize they're not interacting with a file system. They can still use the applications that they have, but if they want to get the most performance out of the new storage system, they will have to change what they're doing and use lower level APIs to access the true performance of persistent memory and flash. So what this means is that we've got to innovate. There's plenty of time between now and 2024 when we deploy, and we are in the process of exploring, who's got the best technologies, what are the right ideas, what's minimally disruptive to our users and their workflows between now and then. But the good news is there's plenty of room for innovation. So things like computational storage are very exciting to us, because there's this notion of HPC has these weird requirements like file systems. How much of that can we offload to a storage device or a network device that we no longer have to support as part of the default performance limited node configuration, for example? There's new NVMe features that are very promising to help deliver better quality of service so users aren't stepping on each other quite so much. But the real challenge here is enabling the full software stack to make use of these new features, because we still do have to provide the software that sits above the hardware that provides interfaces that our users' applications develop against. But the good news is this is not new to us. We've been innovating for the last 45 years, and it's just something we do. So I was telling the group over lunch, NERSC has historically deployed serial number 1 of many systems and technologies. So this is just a timeline of the last 20 years. You can go back further and see a similar record of systems that are pretty risky. Being the first of their kind, they do have problems, and that is why our utilization is high, but our uptime, our availability is not quite what enterprise would have. But that means we can enable breakthrough science that has never been possible by deploying technology and integrating it in a way that has never been seen on the planet before. So some concluding thoughts. Great science takes time, so it's difficult. It's not a procedural workflow like providing a microservice, for example. There's no predictable nature of how many users will show up on Black Friday, say, and want to do something. We just, it's poorly defined what science will bring us in the next 5 to 10 years, so we have to remain flexible. Data is long-lived, workflows are long-lived, so we still support a lot of Fortran code and a lot of applications that haven't seen substantial modifications in the last 2 decades, and those will continue to have to run on our systems for the next decade. We don't have the ability to just turn those users away and say, you can't do your science anymore because we won't support it. And we have these unique requirements in HPC. Data can remain hot because these workflows run over the course of weeks or months, and a campaign can run over a year, and we need to support data that is accessible over the course of that entire scientific campaign. But we're saddled by these performance-limited and scalability-limited data interfaces like file systems. They just don't work at extreme scales. But partnerships and innovation are really at the core of what we do, and through partnership and innovation with vendors and software providers and our users, we're confident that we'll continue on this path of success and deliver systems that will be able to continue to deliver breakthrough science. And with that, thank you very much for your time. And I'm happy to take any questions.